All right, so tonight we're going to be talking about another method to build time series models using multiple linear regression. This is kind of an alternative to ARIMA, and it has both benefits and negatives compared to it, so we'll kind of talk about those. But the outcomes here tonight are to learn to use linear regression to model time series data, and then to also see about building multiple time series at once. This is important because it's something you'll have to do for the Mod 4 project. So in a lot of ways, tonight is kind of a warm-up for the Mod 4 project for you guys. So to start, we're just going to import our basic library as we always do. And then we're going to start with this data set here. It's Australia drug sales. It's basically the cost of a corticosteroid in Australia over time. You can view the head here. It's just a time and then a value column. So we're going to want to make our index a date time. But does anybody see a problem with the format of the time as it is? You can see it's in decimals. So you would imagine, 1991.5 would probably be June, the 6th month, in 1991. So we're going to have to come up with some way to convert these decimals to the month value and then pass that into like to-date time and set that as the index. So we're going to do that now. So a neat trick is you can call .mod off of a column in a data frame, and it'll give you just the decimal places. So we have all those here. And then this next cell, we'll get the decimal places, and then we'll just multiply it by 12 and add 1. And this will basically convert it to a number from 1 to 12 corresponding to the month. And you can see that here. So now we'll create a month column using that same code. We'll round it and just make it an int to make it easy to work with. And then for the year, it will just be the regular time column. And then, let's see, I don't think we need day on here. Let me check. Yeah, I don't think we're actually going to use day, so ignore that. But you can see how month and year have been separated out. So now using both of those, we can combine it into date by passing in, let's take out day here. So passing in year and month to pd.toDateTime, and then we'll just set the index as a datetime index, and then we'll drop all the columns that we don't need. So at the end, let's see. I think I need to rerun this. All right, let's take the day. Oh wait, we actually do need the day. I remember why now. Because when you do the to date time, you have to pass month, year, and day. So we will keep that actually. And then we will rerun this. And we put day back here. And then year, month, and then day. That should work. All right, so there we have the index as our date time, and then we have the values. So it's all set up to work with it as a time series. So we'll go ahead and plot it to get an idea of what's going on. We can see there's a little bit of a linear trend upward, and there's definitely some seasonality. There's this oscillating pattern. We can also see the dates run from about 1992 to 2008, so about 16 years of data. And we know just from looking at the data frame that it's broken up by month. So the frequency is by month. And now we'll do the seasonal decomposition function just to further look at what's going on. You can view that here. So we do see that upward linear trend. We also see the seasonality. Now the seasonality, you could say it's a year repeating or maybe even 6 months. I think for the sake of building our first ARIMA model, we're just going to consider it being a year seasonality. But yeah, so this is what it tells you, and then we have some noise left over. So then we will also look at the ACF and PACF plots. And we can see definitely some significant lags going on here. It's hard to see it because it's cut off there, so we'll go back out. And so on the PACF, can anybody tell me what we can gather from this that's significant? Any patterns that we've seen before? And also combining it with what we saw is going on here with the seasonality.
Does it have to do with the number 12?
Yes, it does.
The after 12 lags, right?
Yeah, so this tall spike here is at 12,
Mm-hmm.
and we can see that it's highly significant, and then it immediately drops to negative. That usually means there's a repeating pattern going on at that lag. So that's what we saw here with the seasonality. There is a repeating pattern every year, every 12 months. So that's just one thing here. And then also on the ACF, I mean, 12 is the highest. So we know that's going to have to be a component in one way or another. All right, so this next part I already ran because you'll see how long it takes. But we're basically going to build an auto ARIMA model using that one library that I found. We're going to set our test period as the last 2 years. So 2 times 12 months. We're going to pass in the data frame up until that test period, the last 2 years. And then at the very end here, you'll see that I set seasonal to true. And then for M, the seasonal component, it's going to be 12 because we want to have that yearly repeating pattern and for it to build a SARIMA model. So we'll just go back out here to show you how long it took. So this took 96 seconds to find the best ARIMA model. It tried all these different combinations. You can see the AIC and BIC here. And then we'll just go ahead and make a forecast. So if you haven't seen this, you take the ARIMA object, you call predict on it, you tell it how many periods. We already set aside test period as being the 24 periods for 2 years. So we'll just go ahead and run that and store it. And then we can import mean squared error and go ahead and calculate the mean squared error for the ARIMA model. So this is just to kind of give us a baseline. This is the main way you've learned to do time series so far. So it'll be something to compare the linear regression way to here in a second. So to start with the linear regression way, so right now our data frame is 2 columns, well, the index and then 1 column. So all we have to work with is the date and the other values in the data set. So from those 2 things, we need to generate some features that we can fit a linear regression to. So a couple things that we can do is generate date time components. So we can take out the year, take out the month, the day if we have it. If we had more granular data, we could break out the hour or the minute. We can also use previous values. So we can add a feature that's basically yesterday's value, a value that's last week's value, last year, so on and so forth. Then we can also add polynomial terms for all of these that we've already made, both the date time components and the previous values. So we can basically just create features where we square those values or cube those values just to give the regression more to work with. Because sometimes there's, you know, an exponential trend there, quadratic trend, something like that. You can also add interaction terms. So maybe combining yesterday's value and also last week's value. Maybe that's significant in determining today's current value. Today we're not going to work with the interaction terms just because it makes the feature set really large. But if you narrow it down a little bit and maybe don't just do the auto one from polynomial features from sklearn, then you might have a better time. But if you just do it out of the box, you'll have way too many terms and basically the model won't fit. So for today, we're just going to be concerned with these first 3. So in building these, we'll start off simple. We're just going to add the year and the month as new columns in our data frame. So you'll notice I did something here. So we'll take the year and then we'll subtract the minimum year. So then our years start at 0 and then it'll go up each time we increase the year. And then the month is just going to be basically 1 through 12 repeating. And then next, we will add polynomials of all of these date time features. So I'm just going to stick to second and third order, so quadratic and cubic. And so for each of our date features, the month and the year, we're going to add a polynomial term for orders 2 and 3. So in the data frame, you'll see what this looks like a lot more clearly. So we have year, month, year squared, year cubed, month squared, and month cubed. And someone is typing in chat. Did you guys get errors on this? Yes?
Yeah, when I run the the previous cell, it seems like min got an unexpected keyword argument access. Is it what you got?
This one here?
Yeah.
Min got, that's weird. And you guys ran everything, oh wait, yes, to fixture.
Yeah, I was not able to install Pyramid.
Okay. Well, here towards the end, we can try to fix some of those installation issues. You can do it the way the curriculum showed, where basically you're doing the same thing the AutoRima does. You just try out all the different ways. So just, yeah, I guess we'll try to figure out a way to fix that for you guys towards the end. But for this problem here, you could just try taking this away. So just do just the year like that. And then let me know if that works. Did that work for you guys?
So just take out the, yeah, that works.
It's probably like a version problem. I'm probably on a different version of NumPy or something. We're getting another chat. Okay, so everyone's good then, thumbs up, yes. All right, we'll continue on then. All right, so now we get a little bit more complicated. We're gonna add previous values. So we're going to add yesterday's value, 2 days ago, so on and so forth, up to a certain range. Arbitrarily, I picked 10 years. So 10 times 12. So for the past 10 years, we're gonna add each of those values. So if we were, actually, let me just run it and show you what it looks like, and then that'll make a little bit more sense. I'm also going to add polynomial terms for each of these, just like I did with the month and the year. So cubed and squared. So you can see here is where it starts. So previous one just means we put the previous month's data here. And then for here, it's the previous month's data. This is basically what we did with differencing. So this would be like lag 1 squared, lag 1 cubed. And this goes all the way up to 119. So it basically stores all the previous values. You'll notice we have the B fill here just so we don't have null values. So in doing this, we generated a ton of features. We didn't even really have to look at the time series to determine any of this, but this will allow us to pick up on significant trends here in a second. So we don't even need to know right now that there's probably something significant on a yearly interval or anything else like that. So now we're going to fit a regression model to this. So I've chosen a lasso model. Can someone tell me why a lasso model might be a good option for this scenario, considering how many features we have? Does anyone remember what lasso regression does that's special? Beth looks like she has an answer.
Possibly. So the way that I remember what the lasso thing does is it like narrows down the field and it picks some of the more significant features that are involved, but I can't remember how it does it.
Yep, so it basically, it allows the coefficients to go to 0. It's trying to minimize the total value of all the coefficients, and it allows some of them to go to 0. So it basically will eliminate the features that aren't important in determining the actual value, and it'll keep the ones that are. And it will prevent overfitting by keeping the coefficients low. And you'll notice this isn't just regular lasso. There's this weird Lars term in here. Basically, Lars is, it's like least least angle regression or lowest angle regression, something like that. It basically also prevents from overfitting. It's just like an improvement on normal regression. And I've just found that this gives the best results. When you're adding this many features, we don't want to overfit our model and just give it a ton of stuff that doesn't actually determine the values we're looking at. And then the CV in here, that stands for cross-validation. So it basically will fit this 5 different times with different subsets of the data, just to ensure that we aren't overfitting also. And so this will try out different values for alpha for the lasso component, because if you remember, lasso has an alpha component that tells you basically how much to penalize the terms. So like with a higher alpha component, you might end up with, I think, more features, but if it's lower, then you'll end up with less. So we're basically just fitting a regression model to our features here, trying to limit how many features end up in the final model. So we'll go ahead and fit it here. You'll notice it might take a second or two, not too long. And now we're just going to print out the features it selected. That's basically all this is doing. I'm just making a data frame. I'm getting the coefficients from the regression, and then I'm only looking at the ones that were greater than 0, because the ones that are 0 won't matter. And then I'm just comparing that to the columns in the data frame to actually get the feature names that it ended up choosing. So if we go ahead and print this out, we can see that, let's see. So month cubed, previous 1, previous 12, previous 48, and previous 60. So the last month, 1 year ago, 4 years ago, and 5 years ago, it determined were the significant things, as well as the month cubed. All right. So now this is the most complicated part. We have to forecast the values in the test period. So right now, that part of the data frame is empty. We have to basically generate each row, row by row. So for each date in the test period, we have to add the year and month values, just like before. We have to generate the polynomial terms for them. Then we have to go through and look at the previous values in the table, all for this one row still. And then finally, we can plug all of that in to our regression and get a prediction on the value. Then we can plug that value into that specific row and then go to the next row and repeat. So we're basically forecasting row by row, filling out the data frame for the test period. So we'll run this. This takes the longest amount of time out of this method, but still not too long. And so now we're done. We're done with the regression method. So you saw it took significantly less than 96 seconds. We'll go ahead and check the mean squared error here. You can see the UREMA, was still pretty good, 0.008, but the regression method actually did even better, and it finished in a fraction of the time. So this isn't always the case. It's not always the better option, but in certain cases, especially when you have to fit multiple models and time is an issue, it can be a good option. So just to solidify this, we're going to look at a couple more things here just to compare. So this is the UREMA forecast versus the actual values. You can see it did a pretty good job. And then we can also check the regression. Maybe did a little bit better. You can see on this second hump here, the UREMA was a little bit off, whereas the regression was pretty close. So both are still decent models. You could use either one probably, but the regression is probably a little bit better. So now we can look at the residuals. So does someone know what the residuals are when you fit a regression?
It's like the error terms.
Yeah, it's basically the error. So it's basically what's left over after you've made your predictions and compared it to the true values. So the cool thing about residuals with time series is if you fit a model and then get your residuals of the model, if the residuals still show seasonality, trend, stuff like that, then you know that your model's not completely taking advantage of all the information that it can get. So we can go ahead and plot the residuals then for both the UREMA and the regression model. Here's the ARIMA. What we want to see is a stationary time series that basically looks like white noise. So it should just be, you know, spikes of data across, kind of like it is down here. But you can see for this first, I don't know, couple years, there's a spike up here. So odds are there's something that the ARIMA is missing in this area. If we compare it to the regression model, we can see this is much more stationary. This is kind of what we want to see. We want our residuals to just basically be the random noise that's kind of impossible to predict. So at the end, the residuals should just be that noise, and we shouldn't see any trend or any seasonality within here. And this is just a good way to check, like, if you're done, basically, if you're trying out different ARIMA models. All right, and then lastly, we'll look at the ACF and PACF. This is another thing. You can plug the residuals into this as well to also see, you know, if there's any significance going on. So this is the ARIMA residuals. You can see we have plenty of values in the ACF and a few in the PACF that are above the significant regions. So ARIMA could do a little bit better. For the regression, we see a little bit better picture. We still see some significant values, but not too many. So again, the regression seems to have done a little bit better job. So we're going to go through one more example doing almost the exact same thing, only with a different data set.
Hey, Matt, before going through this, can we see how many factors came in for the regression? Just curious,
Oh, yeah.
how many features?
Do you mean before, like how many features were generated? Or how
many features were taken in the regression?
Okay, so that is right here. So I looked at all the coefficients that were above 0, so that didn't get lassoed out, and it was only these 5 here. So the month cubed, the previous value 1 month ago, 1 year ago's value, 4 years ago's value, and 5 years ago's value. And you can see 1 year ago being the most significant value in predicting a future value.
So in a time series, is it important that we know the feature, or is not so? It's more like we just care how accurate the prediction.
It depends on your application. I would think you'd always want to be able to get it back into, you know, real terms and kind of understand what's going on. Like, we didn't really think, we only maybe saw that, you know, 1 year ago was significant from the seasonal decomposition and stuff. But this is telling us that 4 years ago and 5 years ago are actually somewhat significant too. So
that means that, sorry, go ahead.
I was just going to say this in a way like tells us a little bit more information by seeing which features it ended up selecting.
Okay. So does it mean that if on the 12 months, that means that it's correlate more with like yearly trend?
It means that the previous year's value is the most significant term in predicting like today's value.
Okay, cool. Yeah.
Yep.
Awesome.
Yeah,
Thanks.
it can also help you rank the features then too, because you can compare them. So.
And using lasso, we don't need to look at the p-value, right?
Right. So the lasso Lars basically will take that into consideration. It does kind of a stepwise regression to kind of avoid features. So it'll only add and keep the significant ones.
Got it. Cool. Thanks.
Yep. Anyone else have any other questions before we do this again? All right.
Actually, I do, because I keep getting an error after a certain part, and it's telling me that the test period is not defined. Is that because that's part of the?
Yeah, it's in the auto ARIMA block, so just break it out and it should be fine.
Okay, thank you.
Yep. All right, so for this example, we're going to be looking at some sunspot data. This is a cool data set because it's a really long time span. It's from basically the 1700s until almost modern day. So we get a month column and a sunspots column. Obviously, we have to convert the month to a date time, set it as the index. This is a little bit easier than the last example. We can just do it all here and then see we have our index as the date time and then our sunspots column here. So we'll go ahead and plot it again, see what's going on. Not really much trend, but definitely some seasonality. You can see there's like a dip here in this time period, but then it kind of increases after that. So if you know anything about sunspots, they do follow trends, but the trends are kind of variable, and it's hard to predict sunspots. So this is kind of cool then, and you can see it goes from 1700s to about 1980, I want to say. All right, and then we'll plot ACF and PACF, see if there's anything interesting going on. We don't see any like sharp spikes at a certain point, so that probably tells us that there's not a very explicit seasonality, but we can go ahead and do, I guess I skipped the seasonal decompose, but we could have checked that too, but the seasonality was basically a bunch of like short spikes. It was hard to gather anything from it, so I just skipped it. So you guys will have to skip this part. This is basically building the auto ARIMA for this one. I ended up putting a seasonal component of 1 year or 12 months. This data is also the same as the other one, it's by month. Let me go back out and see if this is loading. Yeah, so this is gonna have to run for me for a second. I think it should take a little bit less time than the other. So I will just run these cells and kind of walk through them so we're ready when it catches up. All right, so we're gonna do basically the same thing as before. First, we're gonna add some date time components. So in this cell, we're adding just the year and the month. That's basically all we can add. We don't have the day, we don't have any hour or minute values. So we'll add that there. And then we're gonna add polynomial terms for the month and the year. Same as before, just orders 2 and 3. Then we're gonna add previous values. Again, I chose 10 years. This is arbitrary. The more you add, the longer it's gonna take, the more features you're gonna have. But it kind of just depends on the data set. If you think there's something significant beyond 10 years, I'd say, increase it. But I know just from researching it, sunspots have like a 9 to 10 year cycle. So I decided to keep it at 10 years. And then this again will also add polynomial terms for each of these previous values. And then yet again, we're going to do the lasso lars. This time, let's see, did I set the... Okay, so this time the test period is going to be 20 years. Since we're going from the 1700s to 1980 or whatever, we're going to pick 20 years as the test period. We're going to fit the lasso lars. I increased the cross validations to 10 just because it's a large data set. That doesn't matter too much though, 5 is usually fine. And once the ARIMA is done running, this will catch up. So we'll just skip that for now. And then this cell will go ahead and print out the important features that were selected. And then this cell here, we go back out. So this cell here will create our forecast data frame. So just like before, it will go row by row in the test data. It will find all the previous values, add the date time terms. It will make a prediction based on all of that. It'll plug that in, and then it'll move down and compute all the values yet again. So it'll do that throughout the whole test set. And let's go and check on the ARIMA. All right, it is still going. So then we're gonna do what we did before. We're gonna print out some comparisons, the mean squared error, the residuals. I think maybe, I think it's getting close. I think it only goes up to like 3 on the, nope, maybe it goes up to 5. So you can already see how time consuming this is. And this is just for one data set. So imagine if you had to build a remodel for 5 different data sets at once. You can imagine how much time that will add up. So I'll just run all these cells. We're just going to compare the residuals again. And then let's see. Okay. Does anyone have any questions while we're waiting patiently for this? Is this making sense how we're going about this? Can I get like a thumbs up if yeah, sideways if so, good? Everyone's good? Okay. Jacob, do you have any questions? Are there like certain parts? Oh, the pyramid thing. You might have to, I forget what I had to do. You have to like uninstall something and then reinstall. And are you installing like pyramid dash ARIMA? Not just pyramid? Because pyramid's actually a whole different library. Okay, well, we'll take a look at it here at the end, but it looks like we finally finished. So about 5 minutes later, a ridiculous amount of time for that. So we went ahead and made our forecast. And then we already looked at all this. This was just generating the features. This was building the model. So these are the significant features it picked out. So quite a bit more than last time. So we can see things, you know, previous value 2 months ago, and then just some random ones. I mean, 108, is that, I think that's divisible by 12. That might be is learning. It shouldn't matter if you're using the learn environment. The pyramid library isn't included in it. Like you'll have to install it separately, but I'm not sure if there's a conflict with like sklearn or something. So yeah, so these are the most significant features. Let's see, the most significant would probably be the, let's see, the previous one and 2. I guess it goes in ascending order, or yeah, ascending order here. So these were the features it selected. And then this was just forecasting them. What is this error telling us? Okay. So what was our initial test period on the first problem? Does anybody remember?
It's saying like in this, I think it's 10.
Yeah, but on the first problem, was it what, like 2?
Yeah.
2 years. There we go. Okay, so it basically kept the test period for the ARIMA from before, but then we rewrote the new one. So this is a little bit off. The ARIMA is probably a little bit closer if we were to rerun that with the correct test period. But you're going to get a similar result here. The regression is going to be a little bit better. And we're going to get this error a couple times here. So on the ARIMA ones, you just have to replace the test period with minus 12 times 2. But that may not work for our graphs here. So yeah, we might rerun this at the end. I'll rerun it while you guys are doing the activity, and then we can see these a little bit better. So Brendan, did yours work then?
Yes, I just got it working.
Okay, so maybe try what Brendan did there in the chat.
Yeah. Here, I'll send you guys what I added.
Yeah, I remember having to do this when I updated NumPy.
All right, any questions before we go on to the activity here? I know you guys are wanting to get the pyramid thing working, but just give it a second here. All right, so for the activity, you're going to be basically doing what we did. You're going to be using stock market data that has data on various stocks. Only in this case, you're going to have to build a regression model for multiple stocks. So this is going to really prepare you for the project. So in this data set, you're just going to use the close column. It's basically the closing value for each of the stocks. And for each of the stocks, you want to build a model. And ultimately, the goal is to be able to predict which stock is likely to see the biggest increase, to know which one to invest into. But you don't have to go that far if you don't want to. This might take like too much time. But the goal is just to kind of prepare you for doing multiple time series modeling at once and to compare them. And my suggestion is just to use the most recent year of data as your test period. All right, and then I have just like 5 steps here. I'll let you guys read through them just to give you kind of a game plan here. And then the bonus is determining which stock is likely to gain the most value, which one we should invest in. And then that's it for that. Since I know some of you hate scrolling up and down, I added a table of contents so you can go back up to the examples and see the different parts we did here. And so, and then I also commented this out with kind of instructions for each cell. So does anyone have any questions before we do breakout rooms? Nope. All right.
Okay, so first thing we did is we read in our data here. Because Matt told us to look at the close column for our predicted value, or for our values, we went ahead and dropped low, open, high, and volume. So after you're done with that, I went ahead and split the stocks into different data frames based on what the stock is, and then appended it to a list here that I called stocks. If I had to do it again, I would maybe hold off on splitting them until I've done all the data transformation that I'm going to do, and then split. So then from there, what we do is we change the date values from strings to date time here. Or I'm sorry, I think I did this first and then change the index to that and then split. That's what I did, sorry. And then that ended up being in reverse order because my code got messy. And then what I did is I iterated through each of my data frames here in the stocks list and did some feature generation. So stock year is equal to stock.index.year minus the numpy min, numpy array, stock index year. And then we did month and day as well because we actually have daily values with the stock prices. And then I saved the list here of date features. Next, we did the polynomial terms. We did 2 and 3. So again, I kind of just wrapped this all in a for loop. Then did feature and date features, I and polynomial terms, and created feature generation for all the polynomial terms here on the dates. And then when we went here and we were backfilling previous values, our previous value range we set to 30 because we were doing day, so we decided to use 30 as like a monthly period. And so from there, we just basically did the same thing, loop through here, create all these features. And so then in order for the lasso Lars CV to work, you can't pass in the names. So we went ahead and dropped the names here from all of our stock data frames. And then from there, we import lasso Lars CV, set up our 3 models here. the way we did it is we dropped the prediction value for our independent variables, and we looked at everything where the index was not equal, the year index was not equal to 2017. And then we used the close values as our dependent variable. So we did that for all 3 stocks, as you can see here. Then we took a look at what some of the features were and what features the models decided to keep. And then what I did here is I basically just saved the models into a list of their own. So when I went and iterated through here, what I could do is I could take each of the models and each of the stocks and match them appropriately. And so we used the code that Matt had written earlier to kind of get these prediction values, just substituting instead of value, we use close. And then for all of our predictions, we end up using the 2017 year here. So after we take a look at all of this and we append then I end up saving all of the forecast values into another list called forecast stocks. What I ended up doing is I ended up iterating through again, taking the real values from our actual stocks data frames, and then looking at our predicted values, looking at the difference for those, printing that out. And unfortunately for us, I mean, sometimes we got relatively close, although the stock price is $54 is quite a bit off. And that's kind of where we got. So we got to at least some sort of prediction, but in this case, we found ourselves not getting the most accurate model. So per Matt's suggestion, our next step was to maybe shorten the test period to a single month so that it's not having to try to project stock values over such a long period of time.
Yep, and just thinking about the nature of stock data, it's probably most dependent on the most immediate and previous days. So if we're setting that aside and not training our model on that, it might not make the best predictions. So that kind of just goes into, the different types of time series have different drawbacks and, the methods you end up choosing. So I think I'm gonna have this be kind of homework. I'll share the solution on Wednesday, but I'll give you guys a chance to kind of finish up, maybe try and make some final predictions for the next day and see how that works out. And then on Wednesday, we will be starting the Mod 4 project. I'll kind of get you started with a starter notebook and then give you guys some time to kind of collaborate and work together. All right, any questions before we go? Nope.
Nope.
All right. Yep, Brendan.
No, I just was saying no.
Oh,
Sorry.
okay. All right, well, thanks everyone, bye.
All right, thanks, Matt.
Yep.